Okay, so good evening, everyone. I'll just start the class. So this is the sixth tutorial session on the NPTEL course of Mechanism and Robotic Kinematics. So I'm Krishna here. So keeping in line with what we have, the format that we have adopted so far for our tutorial sessions. So in today's session also, I'd be reviewing some very basic. So yeah, I'll be reviewing some of the basics of week 5. Of week 5, and then we'll also be discussing some of the special topics that I had mentioned in the last session. It is from a review paper. It's just some write-up, but a very excellent write-up on representing attitude, and it talks about various different approaches to uh, define the angle representations for a rigid body system. Right, so I'll just take I'll spend a little bit on velocity analysis and the geometric concepts in today's session. And then we'll fully discuss at length about the special topics that we'll be covering, which are transformation matrix, pose of a rigid body, the coordinate rotations, I believe it's coordinate system, coordinate rotations, yeah, and then direction cosine matrix, basis vectors, and rotation matrix multiplication. Okay, so let's start with just reviewing some of the aspects of week 5 today. And so as we recall, what do you mean by velocity analysis? So that's where we start. So for velocity analysis, what we do is, say, given any mechanism, we need some actuator to affect some output motion, right? So far we had been discussing about a static case in the sense that static in the sense that we only look at the orientation of the actuator and the resulting output, and not how it varies with time. So it was just the final what would it be the final input and what would be the final output, rather than the process of, say, its behavior with respect to time, isn't it? So in this case, what we do is in velocity analysis, so given certain actuator velocity input, what is the output velocity, right? So that's what we are looking at in velocity analysis. So essentially, that's what it is, right? So now, as in the previous cases, we will be talking about forward problem, which is given actuator rates, find output velocity. Find output velocity. Inverse is, of course, as the name suggests, here for a specified output velocity, find the actuator rates, right? So there's what it is. Okay. Now in what we call as the in the robot velocity analysis, isn't it? So that's what we are one of the things that we are looking at. In this case, the velocity vector direction decides end effector path. So here, since in robot the end effector happens to be unconstrained in the sense that it's free, not unconstrained, it's free, right? So here we would like, and it's able to move freely in space with um, based on again the internal constraints at every joint. So taking that into account, so we will always have a path, right? So say we have some robots say, right? Some robot, and this is the end effector. So based on certain input, say if it's theta 1 we are providing and there is some theta 2, based on this can move in space, right? Certain it will follow some path, say some path arbitrarily, right? Some path, but which can be determined if you do a systematic study, but will be able to determine those paths. So here the goal is in forward problem, we are looking at if given actuator rates, we are to find path velocity, right? An inverse plane. So, and in inverse problem, and this is actually a major part of what we do in robotics, what we call as the path planning. So the idea is for a specified path velocity, find actuator rates, right? So that's what we do here. Now, in today's session, we would also be looking at, so we start with say motion of a planar rigid body. Right. So what we do here is, say we have some planar rigid body in of this sense, right? And we have say 2 points, A and B, with individual velocities. Say at the point, say at A we have, I'll just use a different color. So we have VA, and then we also have say VB. And there is some planar rigid body, right? So this is planar rigid body. So here we have certain conditions on velocity as well. So condition on VA vector and VB vector. in that they cannot be just be arbitrary. It has to satisfy certain requirement, isn't it? So the requirement is that, say we look at the relative velocity. Say we fix our gaze, right, on point A. So taking A as the reference, then the relative velocity of B with respect to A is what? So we'll write it as B by A, notation wise. This is equal to V vector V minus vector A. Right. So this is the relative velocity. Now let's just take and then also let me call as the say the or rather I would call it relative Poisson vector. I think that is the best word here. So the relative Poisson vector of B with respect to A is, we'll call it D vector B by A is equal to, say we have some, say this is the origin for some Euler. Since we are dealing with planar, so I'll just take X and Y coordinates. And let's call this as this Poisson vector as X vector B and this as X vector A, right? So this D vector, which is essentially this one from here to here, right? With the tail at here and the head at here. So this will be dB by A vector. So this is equal to X vector B minus X vector X vector. This will be right. Now let's just look at the relative velocity that we have been talking about, right? So say before that, let me tell you something in the sense that now let's look at let's look at this quantity and just a moment. Right, so let us take a look at the quantity called VBA dot product of VBA and DBA. Let's take a look at this, right? And then just let me redraw this figure again. So we had A, B, connect line, that line, I mean vector connecting A and B is D vector BA. And this is VA, and this is say VB vector. And say VBA minus VA vector, right? Is it what we had VBA? So like say, suppose we just translate this vector here, this one, and bring it to here, such that the ends meet. So say in such a way that the ends meet. Right, so the end is meeting in the sense that okay, so there's VB vector, this is VA vector, right? So this will be our VBA vector, isn't it? From the triangular sum rule of vectors. Right, so this is what we have, VBA. Now, say we extend this DBA vector here like this, and we find that right now in the image, I mean schematic that we see here, that when we have VBA dot DBA vector, and we find that there is certain component. So this is the component. So this the dot product will give this, right? This quantity here, some length, right? So which means that if that is so, then what we see is, say if is not equal to 0, if it is some value, then what happens is then point A is moving towards point B. This implies that, not so as to be not confused, distance between A and B is either reducing or say increasing, which means that dBA, the norm of this, is not constant. If it is not constant, it means that the assumption that the body is rigid, which means that this body, I'll call it say body C, capital C, right? So C is not a rigid body, because in rigid body we do not allow relative motion between the points. So the distance between points and the angles, yeah, the distance between any 2 points does not change in a rigid body. So which means that, therefore, based on this argument here, for C to be a rigid body, VBA dot D vector BA has to be 0, which means that VB minus VA dot say XB minus XA has to be equal to 0, or in the sense that, or this even implies that the relative velocity, right, has to be perpendicular to, right? So that is the thing, that our VBA has to be perpendicular to DBA, right? So this is one of the I mean the condition for the, and this implies that this given VA and the distance VB, this the what you call the condition on vector B is such that it has to follow this requirement. This is the requirement it has to follow. So VBA cannot be arbitrary, it has to satisfy this relation. And it is satisfied if it lies on a line perpendicular uh, to this here. So to perpendicular to a distance, I mean to this vector dBA, and if the velocity head, I mean velocity vector head lies of B lies on this line, then we'll be able to satisfy uh, this condition here. Provided that there is certain, I mean, requirement on how much extent it can go from B to along this line. But apart from that, the thing is it can only lie on this particular, say, axis, which is perpendicular to the displace, I mean, the relative Poisson vector of point A, B with respect to A. So that is what it was. Now what we are looking at is, say we have 3 points. So say given 3 points, say I draw a rigid body, planar rigid body, and right. So I have this planar rigid body. There are A, C, and B. And we have lines connecting A to C and C to B. The velocity at a point A is this, and point B is this, right? And we are to find what is the velocity vector at C, right? So in this case, what we do is we extend this line connecting C to B, extend it further, and take this projection of VB on this one, right? And then translate this vector here to here. So we'll have certain, so this is our, the projection of velocity vector VB on the line connecting point C and B. Likewise, at point A, we take the projection, orthogonal projection, I mean, orthogonal projection of velocity vector VA on the line connecting points A and C. So this is our vector, the orthogonally projected vector of VB on the line connecting A and C, and then just let it translate it and then have its origin fixed at C. So something like this, right? And what we do now is draw a line perpendicular to the tip of this vector, perpendicular to this vector at the tip. So you have this, and we have this. And this is our intersection point of both these lines, L1 and L2, right? And we connect this intersection point with the point C, which is essentially this. And this is our velocity vector C. So this is how we determine the velocity vector of at any other point C, provided we know the velocity vectors at points A and B, isn't it? Now, this was one case which was discussed in the class, and there was um, another such example where it was given that we had these 3 points, three non-collinear, I mean, they are all non-collinear points, A, B, right? We join this A, B, C, this B. And then what we have is, say we have some velocity vector VA. And this here. And this velocity V vector is perpendicular to the line connecting the points C and B. Right? So what we have to do is we have to find again the velocity at point or the velocity vector of point C, wasn't it? So what we say, given that we have this perpendicular, which means that velocity VB has zero projection on the line connecting point C and B, because of which all that we can do is we can just, right? So all that we can do is just take a line, I mean, have certain velocity vector, which we know the direction that it has to be parallel to. We have to have it will be parallel to this vector will be parallel to VB vector, but the length. So to determine the length, of course, we'll require the values of point velocity vector at point A. We'll orthogonally project on the line connecting points A and B. And so we'll have this projected vector here. Translate it here and fix the tail at point C. And what we do now is draw a line perpendicular to the to this vector at the tip, extend it, let it go endlessly on both sides. That's what I mean. And then what we do is along this same direction, we'll just allow it to extend parallel to VB till it intersects. It intersects here, this line. It touches the line. And this is our velocity VC. That's how that's how we were able to obtain. Right. So our next thing that we plan to do is the initial what we call as the instantaneous center of rotation. So let's talk about instantaneous. Right. So what we do is, again, let's pick up, let's consider rigid planar body, and then consider, say, 2 points A and B with certain velocities VA and VB. And we need to find, there will be, say, some point about which at which there is no velocity, or a point, it may be inside or outside the body of this body, capital big C here, where which would not have any velocity, so to speak. or it would seem that the body is rotating about that particular point, and it could lie within or outside the body. Fine. So how do we proceed to get that? So the idea is, say, draw a line perpendicular to the velocity vector VA. I'll just use a different color. And likewise also have a line perpendicular to VP at point P. Right? The intersection of both these lines give us some point C, about which it would seem as if the entire body C is rotating. And this also implies that uh, this point C does not have any velocity. If it is within the body, then it would not have any linear velocity. Sorry. And if it's outside the body, then it would seem that, of course, we cannot say how can a point outside of the body have any velocity, right? So that how we say is, it would seem that this entire body is rotating about that particular point, right? So it would seem as if body is rotating. Um, of course, conventionally we'll have some with some omega c, and this happens to be also fixed at an instant, right? And here vc vector is equal to 0. And this is what we call as the c is known as the instantaneous center of rotation. Now the question would come is, how do you define? The question arises, how do we obtain omega c, or the angular velocity at an instant, right? Now for that, going back to our what we had learned in, I think, in class 9, I believe, was about from the circular motion. In circular motion, the way we define, say you have this point here, right, which is fixed, and you have a string. Suppose you're just rotating the string by holding it. And again, let me rotate in this anti-clockwise fashion. And at this, and you have certain mass m here, some ball, say some object which is just tied at the tip of the string, and you are rotating with some velocity omega. And then because of which there will be some this linear velocity at tip, which is of course perpendicular to this, to the points which is, say, point P, and in the tip of this string, it will have some linear velocity v, which will of course move in a circular fashion, right? Now, how do you define omega for given v and of course the end-to-end distance? So the goal is that, say, this point, we'll call it as q. Sorry, it's okay. So this was p, this was q, and this was some linear velocity v, right? So the way we would define the relationship between v and the distance between p and q, I'll just let me call it L. So v is equal to L into omega. And this implies that omega is equal to v by L, provided v and L are both known. So this was what we had learned in our when we had learned about circular motion. So the same idea will apply here, of course. So omega c is equal to v velocity, the magnitude, divided by the distance between A and C, so DAC, which is the same as velocity of B, of course, since body is rotating about this point C, right? So divided by, again, the distance between C and B. So this is how we had learned, right? Now, this was for, say, in which for any 2 points with its own arbitrary velocities at both these points in the planar rigid body. Say, what if you have a rigid body VA, I mean this points A and B, and the velocities are parallel, right? So what if the say the velocities are parallel, right? So in this case, what we'll do is we will join this points A and B, right? And then what we'll do is, and of course, this will be perpendicular to each other. I mean, to this line joining A and B, because of course there is no relative motion load and both are parallel. And even if they are not, doesn't matter. Why? Because VA, no, let's just see. Let's see. Okay. So say we have VA vector and VB vector. So the condition here also has to be that for rigid body motion, VA, say VA minus VB dot distance between A and B has to be, of course, 0. So in that case, so we extend this and it's parallel, so it will be somewhere here. So the relative motion will be this part, then it has to be perpendicular to 0, right? So this relative motion has to be perpendicular to 0. Because of it, then of course, both individually, both the velocity vectors have to be perpendicular to the vector dVA. So this will be perpendicular, right? Which can be just it's a simple argument here, right? So in this case, these are say are all at right angles, and we want to find the center of instantaneous center of rotation. All that we do is connect both the tips of these vectors and it extend it till it intersects the line passing through points B and A. And this will be our point C, about which the body rotates with some angular velocity omega. Right. So with this, I believe I'll just we'll start about the special topics since we want to devote some good amount of time today. And so I'll just first revise. So what we had discussed last time. So last time we had talked about coordinate systems. So I'll just call it review. Right. So we had talked that there are at least say two coordinate system to describe say the motion of bodies, right? Of course, world coordinate system is good enough. So world coordinate system is also called as inertial coordinate system. And the reason it's called the inertial coordinate system is that in this coordinate system must either be stationary or it can undergo a uniform velocity, which means that this coordinate system must not accelerate, right? And we denote origin by x vector w. So w subscript indicates its world coordinate system. And second is what we call as the body fixed coordinate system, right? And then the property about body fixed coordinate system is, as the name suggests explicitly, that it is, of course, fixed to the body. And which we would like to say investigate, analyze, or study, right? And in this case, we denote origin as, and there are no such conditions on this body fixed coordinate system that it must be inertial. No, so it can accelerate, doesn't matter. It can be rigid, sorry, it can be stationary, and it can undergo uniform, non-uniform velocity, doesn't matter, right? And in this case, we denote origin by xb vector. And this is, of course, with respect to the world coordinate system, right? So once this is done, now let's talk about rotation matrices, which is again, we are reviewing some of these aspects. So what is a rotation matrix? So rotation matrix is a matrix, say, denoted by R. It belongs to spatial orthogonal group of third order, which means that it will be a collection of 3 into 3 rotation matrices. And the properties are that determinant of R is equal to plus minus 1, and R transpose is equal to R inverse, or rather R inverse is equal to R transpose. That's right. However, for rigid bodies, we only consider, or maybe uh, for rigid body transformations, I think that's a better word. For rigid body transformations, those are with determinant plus 1 is only valid. So it means that those are whose determinant is minus 1 are not, cannot be used for rigid body transformations, right? Once this is done, now let's just understand what R is. So R is a collection of, say, 3 vectors, and then with these are all 3 column vectors placed one after the other along a row. And of course, its expansion would be R11, R21, R3, 1. These are the components of R1 vector. For R2 vector, we have 1, 2, R2, 2, R3, 2. For the third vector, we have R3, R1, 3, R2, 3, and R3, 3. Okay. So these are the components of and we see that there are 9 components, which comes from 3 into 3 is equal to 9 components of R. And we later learned that only 3, uh, or rather, R has only 3 independent coordinates. We later learned why, right? So till we have reached this point, now let's start for what we are planned to discuss today. So we'll start with coordinate systems. Coordinate transformations. Right. And what we do is say. So say we have graphically. So this is X, Y, Z. And this is the inertial coordinate system, which is the world coordinate system. And we have certain body in which we have this X, Y, Z. It will be some arbitrary values. And of course, they will also be following the right-hand rule. So now, and let me call it X prime, Y prime, and Z prime to distinguish it. Now say we have a point P. Say we have point P with Poisson vector sorry, with say Poisson vector or maybe I think this will make it more a bit complex. We'll discuss about this in some time. Say we have a vector. So let this be vector P or vector P, right? So say we have a vector. This just to make P with coordinates Z vector. In terms of the world coordinate system, right? And which means that Z vector is an element of R3. And say we want it to know its description. Sorry, it's just start. So in terms of world coordinates, that's what I meant here. Or with respect to rather, with respect to the world coordinate system. And of course, Z is an element of R3. And say we would like to know its representation in the body coordinate system or body fixed coordinate system. So we would like to know its representation in body coordinate system, right? So in that case, Z vector prime and with coordinates, I'll just call it with coordinates Z vector prime. So Z vector prime is equal to R into Z vector. So in that case, the way I should write is not like this. I should actually call it something like this. In the sense that the origin for both the body fixed coordinate system and the world coordinate system must be the same for now. For now, right? So, and then again, for vice versa, if you want to express Z prime, Z in terms of Z prime, uh, right? Or yeah, Z in terms of Z prime, then all that we need to is multiply both sides by R prime. Sorry, R transpose, which is also R inverse, right? So maybe R transpose R inverse Z prime is equal to R inverse R into Z vector. And this comes to identity and R inverse R transpose. So this means that Z vector is equal to R transpose Z prime. So this is how we can go vice versa. And this was only for vectors. And what if we want to transform points? Coming back to the that we wanted to discuss some time back. Say we want to represent a point, or maybe say we want to transform a point in, say, from one coordinate system to the other. Now, in that case, we will have to, again, since this is valid for any arbitrary vector. And it's lying freely in space. But say if we are to transform a point from one coordinate system to the other, in that case, we need to first find an equivalent vector, right? So say you have this coordinate system, x, y, z, and you have this point P, and say the origin at say xw prime, and say x vector w, which indicates the origin of this coordinate system. And then we have, say this has the Poisson vector of P with respect to xw, right? So in that case, we first determine the relative velocity vector, or sorry, the relative Poisson vector of P, the origin. And that will be something which will be something like say to speak freely, right? It should be a free vector in space. That's what I mean. So from this point to this, right? So this is the vector that we are looking at. So this would be given by xp. So this will be, say, some xp vector minus xw. And this will be what we'll call x vector pw. And now this happens to be a, say, freestanding vector, because now we looked at, since it has a what do you call, so it has its end here and the head here, right? Now it looks like some free vector upon which we can apply a, right? So here what we can do is okay, I think I was slightly mistaken here. Just going back. Okay, so the idea is that it has to be expressed in terms of the say there is some separation. Now here we didn't talk about that. So I'll just go back here. So the idea is, say, what if it is at some other, so coincident, right? X prime, Y prime, and Z prime. Okay, so there is the case we are looking at, because otherwise it would have been already trivial. So in this case, and this will have a origin will be X vector B, right? From the origin of this body fitted coordinate system, body fixed coordinate system, right? So in that case, we first determine the relative Poisson vector of P with respect to the origin, sorry, of the body fixed coordinate system. Yeah, now it makes sense. So we'll have X vector is equal to XP vector minus XB vector. So essentially, what we are looking at is this vector. So we have just offset it, right? And now what we can do is, now we can apply coordinate transformations directly on this. So it will be X vector prime is equal to R vector of X prime X vector, right? So this implies that X vector prime is equal to R into XP minus XB. And this can be written as R XP vector minus R XB vector. And we can also write this X XP vector plus X. We have not introduced a new quantity. I'll rewrite this. So X prime vector, which is essentially the representation of, say, the point of vector, point vector, say vector P in the body fixed coordinate system. This is equal to R into XP minus XB vector. This is equal to RXP vector minus RXB vector, and this can be written as XRXP vector plus XW vector prime. Now here, say XP vector is equal to 0. Then this implies that X vector, this one, is equal to XW vector, and this will be equal to minus R XP vector. So this means that XW vector prime is so the representation of origin of XB, some sort of like that, in terms of the say, so if it XB happens to be some 0 point here, then XW prime is the representation of the origin of the world coordinate in terms of the body axis vector. I mean, in terms of the body fitted coordinate system. That's what this implies, right? And now going back, so this is essentially representation of origin in origin of the universe of the world coordinate system in body fixed coordinate system. And say moving back, and say if you want to express XP in terms of the quantities that are well known now. So in that case, what we have to do is say we have X prime is equal to RXP plus RXW prime. This implies that XP, this can be written as XP is equal to R transpose X prime minus XW prime. R transpose X prime XW prime. And as we recall from this equation here, that R transpose XW prime is equal to minus XB. So this is equal to R transpose X prime plus XB. So this is how we move to and fro, back and forth, right? Okay. Now we talk about transformation matrix. Now in transformation matrix, what we do is we use or we represent both rotation it's happening today several times. Don't know what's the reason. So idea is we represent both translation and rotation in a matrix. This is what we call as the transformation matrix. Going back, right? We had this expression here. So say for a generic point, x vector, right? Point vector, x vector, right? So we could write x prime vector is equal to r x vector plus xw prime vector. And we could write this as also in terms of, and also add something called 1 is equal to 1. These two can be combined. And say here we have 0, some 0 vector, I mean, some 0 vector, of course, and then x vector. Of course, this would result in 0 anyway. We can combine both of these to give us a nice looking transformation. X prime 1 is equal to r, then we have xw prime 0, 1, and 0, there's a vector transpose 0 transpose, and then what we can see is x vector to 1. So let's look for the first equation. X prime is equal to r x vector plus xw prime vector. And for the second, the vector here. For the second, this one entry, we have 1 is equal to 0 transpose x vector is nothing but 0 plus 1, right? So this we have is there's a vector of size 4, and this is r is 3 into 3, and x prime is 3 into 1. So this makes it, the columns are 3 plus 1, 4. Likewise, 4 rows, we have, this is 3 cross 3, and this is 1 into 3. So we have rows is 3 plus 1. So there is a 4 into 4 matrix. And likewise, there is also 4 into 1. Right? And this is what is called as the transformation matrix. And this is widely used in this in robotics community, right? And this was for the representing coordinate vector in the Poisson vector in the what happens is in the world coordinate system in terms of the body coordinate system. For vice versa, what we have is, as we learned here, that xp, for a generic it will be x, right? So x vector, just x vector is equal to, sorry, x vector r transpose x prime plus xp. And we have 1 is equal to 1, of course. So 1 is equal to 0 transpose x prime plus 1. And this two can be combined to write as x vector 1 is equal to r transpose, right? And then say, and xp was given as minus r transpose xw, right? So we can write this as minus r transpose xw prime, and then we have 0 transpose 1, and this will be x prime and 1. This is how we move back and forth between both these coordinate systems. Now let's talk about pose of a rigid body. So for pose of a rigid body, it gives us, or it is the pose is the position and attitude of of the rigid body. Say it is defined, of course, for any rigid body, so it will be the position attitude of the rigid body, right? And as we learned, this was essentially the pose, this and this, right? In terms of the relation between x in say body fitted coordinate system, or in the universal or the world coordinate frame. Now let's talk about coordinate rotations. In this case, in general, fundamentally what we have is fundamentally a coordinate rotation is a rotation about a single coordinate axis. This is fundamentally, right? This is how we define. So say we want to say we have this coordinate system here, x with xyz written, right-handed coordinate system, of course, right? And we want to say rotate about x-axis, is a different color, in an anticlockwise fashion, y also in anticlockwise fashion, on z also in anticlockwise fashion, right? And we'll denote as rotation about x-axis for its rates, and just wait. So rotation about x-axis is, we denote with y with 1. Rotation about y-axis, we number it as 2. Rotation about z-axis, number with 3. So, and we denote any coordinate system, and this we can call it I is equal to 1, 2, 3. And we have any rotation about any particular axis as the operation will be Ri, which maps R vector, any point in R space to S. And R here denotes angle of rotation or space of the angle of rotation, right? So say we have R1 alpha. So alpha is the angle of rotation about, say, x-axis, because here the subscript indicates the rotation is about x-axis. So the idea is here the rows of the R1, ROWS. That's what I hope we do not confuse with ROSE. So the rows of R1 will be the representation of the rotated coordinate in terms of the world coordinates, right? So it is 0, 1, 0, 0, and then you have cosine alpha, sine alpha. This will be 0 minus sine alpha, cosine alpha. So this is x prime with respect to x in world coordinate system. This is y prime with respect to y in world coordinate system, and this is z prime with respect to, sorry, it will x prime with respect to world coordinate system. That's what I should say. With respect to world coordinate systems, and to x y prime with respect to world coordinate systems, and z prime with respect to world coordinate system. And this is what you will find the representation. For R2, and say given an angle alpha, which is now the angle of rotation about, say, x-axis. Sorry, in this it will be rotation about y-axis. The representation is, again, the rows denote the representation of the rotated x, y, z in terms of the world coordinate system. So it will be cos alpha 0 minus sine alpha and 0, 1, 0, and this is sine alpha 0 cosine alpha, right? Likewise, and this is again x prime in world coordinate system, y prime in world coordinate system. So in this case, we see 0, 1, 0 because the y, even after rotation, it will be the same, right? Because we are rotating about y-axis, right? And here z prime in world coordinate system. Likewise, the rotation about z-axis gives us, it will be cosine alpha, sine alpha 0, then minus sine alpha, cosine alpha 0, and then 0, 0, 1. Again, the same thing, x prime in world coordinate system, y prime in world coordinate system, and z prime in world coordinate system. And you see that z prime is the same as z because we are rotating about z-axis, right? Now let's talk about what is a DCM. The direction cosine matrix, and also known as DCM, which is very powerful. It's a very indispensable tool in rigid body dynamics. And of course, in robotics or any rigid body dynamic studies, right? So we call the rotation matrix or maybe any rotation matrix can also be called as a direction cosine matrix, DCM. And the reason is why we call it direction cosine matrix is because, right? Because the elements of this matrix, elements of rotation matrix, say R is equal to, we had R11, R21, R31, R12, R22, R232, R13, R23, and R33. Right? So the elements of this are here. of R are the cosines of the unsigned angle between the body fixed axis and the world axis. Right? Now say, let's go to the next page and try to decipher what we mean here. Right? So ideally, we denote the world axis by x, y, z, right? And the body fixed axis by x prime, y prime, z prime, right? Now say we denote x theta x prime comma y to be the unsigned. Now unsigned means we are not looking at whether it's positive or negative, right? So it should not have any, so to speak, sign in front of the number representation of the angle, right? To be the unsigned angle between the x-axis, x prime axis, and y-axis. So this is how we represent things, right? If you go by that, then ours will be equal to cosine of theta x prime comma x, and here will be cosine theta of y prime with respect to x and cosine theta of z prime with respect to x. Sorry. Now, likewise, in the second column, we have cosine x prime with respect to y, cosine theta y prime with respect to y, and cosine theta z prime with respect to y, or with between the axis x prime and y. And in the third column, we have cosine of angle between x prime and z axis, cosine. In this we have cosine y prime axis and z axis, and this is cosine theta z axis, z prime axis, and z. Right. So this is what we actually mean. And using it, we can construct any other rotations just based on this, right? All the elementary elementary operations can easily be deduced based on this. Fine. And then we had to talk about basis vectors. Right. Now, the rotation matrix can be thought of as the matrix of basis vectors that define. Yeah, so there is the important thing here. that define the world and body fixed coordinate systems, right? So here, as we talked about, this row, first row, second row, and third row, right? So first row, uh, the rows are, so here I'll call it rows of R are the basis vectors of the body fixed coordinates expressed in world coordinates, right? Likewise, say when R is equal to, and the columns, say first column, second column, third column, right? So here we'll have it that columns of R are the basis vectors of vice versa, right? Of world coordinate systems, world coordinates in body fixed coordinates in terms of, yeah, right. So there's what it is. And as for the last topic that we had to discuss today, we were to talk about rotation matrix multiplication. So here what we do is, say we have a rotation matrix alpha, and when we have into beta, into say gamma, and likewise, the when applied sequentially from say some delta, something like that, right? Applied sequentially on something, right? So this is equivalent to applying some rotation matrix on that thing. So it's like this implies that R is equal to R alpha dot R beta, R gamma, say till R delta, right? So it's like this is how we multiply. So the product, the multiplication of two or I mean say we start with two rotation matrices that will give us another rotation matrix whose net effect is a combined effect of both rotation matrices, and it's like sequentially applying it. So here it's as if we are applying R delta first, then something else, till we reach R alpha. Right. So we sequentially apply. So in the sense that we have say Z prime, if we have Z prime is equal to RAZ vector. So this implies, and then we have say Z double prime is equal to RB with respect to A, Z prime. This can be written as RBA into RAZ vector. And this we can have as write it as RB into Z vector. Right. So it's like this is equal to RB. And this is what the net effect is. RB is equal to RB by B with respect to A and N. So it's like we first apply first. So it's like apply the rightmost rotation matrix first. On the vector that we want to transform. Yeah, so I think this was what we were supposed to discuss today. And so in the upcoming tutorial session, it would be much more interesting that we would be discussing uh, some of the important furthermore about the kinematics. So in the next section, we will be discussing about kinematics, and then we'll be talking about the notations, the motions of a fit. So we'll be talking about the notation, right? And then also about motion of a fixed point on a rigid body. Right. And then if time permits, we will also discuss about finite difference approximation. So this is in the upcoming sessions, right? Upcoming sessions. And once this is done, then we'll move further into, we'll talk about Euler angles, but that will be, I will better save it for this, the second relative tutorial session from today, where we'll be talking about Euler angles and if possible, you can even talk about Euler angles in the next tutorial session. Then we will be moving to Euler rates, and we talk about Euler angles sequence. We'll have a separate session for that. And then also we'll talk about the quaternions, and this is as we gradually move forward, right? So yeah, I think this is what I had planned. So I'll just stop recording for today, and then let's meet in the next tutorial session.